Okay, so first thing that we're going to talk about, though, I gave you the introduction right before lunch, so I'm not going to rehash on that. There's a couple of types of statistics or things you'll hear, like categories of it. There's descriptive statistics and then inferential statistics. And we're going to start with descriptive statistics. This simply describes the data, hence the word descriptive. So descriptive statistics is going to give us there's going to give us these three major pieces here: location, shape, and variation. And I like to cover them in this order right here. But the first thing we're going to cover is location. And with the location, when we did our capability report and we printed out this data sheet here, location simply means where is my data located in relation to where it should be. Whatever you call it, the measures of central tendency. And so the mean is the one that you're most used to, right? That's one that's pretty important here. And the mean gives us our center point. And the mode, which is the mean, is all the numbers added up, meaning all these numbers added up, and then divided by the number, right? Just simply adding all these numbers up and dividing by the number of data points. So if we have 535, you can see this is our center point, right? This is the center of that distribution. And so 535, terrible writing. But what does that mean at the end of the day with all that stuff I was just talking about? Why do we have to know our measure of central tendency? Why do we have to know where it's located? We just simply have to know because guess what? It's supposed to be at 135. So I have to know three things about my descriptive data when I'm describing my data. One is, where's my data located? My data is located at 535 if I'm team A, and it's located at 473, right here, 473 if I'm team B. And where is it supposed to be? Yep, 135, that's right. So it should be 135, and we're at 473 or 535. Cool, that's step one, right there. Where's my data located? And now the next thing we look at, I gave kind of a lead in with some of the other things I was talking about. Let's go to the slides, make sure we're hitting what we need to. The next one is going to be our shape. Let's play around with some slides. This is a normal distribution. A normal distribution is that bell curve, something that represents a bell. Well, let's take a look at our data. Do we have a bell-shaped data? Do we have bell-shaped data? So if we look at this data, if you notice, Sigma XL or Minitab or whatever software you're going to use actually draws that line for you, like the shape. Do we have a bell? Does it look like a bell shape, roughly speaking? Yeah, okay. I would say visually it looks like it's a bell shape, right? Pretty dang close. So we can see, so when we're talking about a shape and you say, well, why does shape matter? Shape matters because if we have normal data or non-normal data, the calculations that the computer does with it later are different. It's doing visual right now, and then we'll go back to that piece. What about for team two or team B, excuse me? Does this represent a normal distribution?
I'd say no.
Okay, and then somebody's saying no, kind of looks like it tails off to that right-hand side. So there's what's cool about this is there's actually a way to tell outside of visual. Visual is one way that you look at it, but that's not really going to give you a good answer. I'm going to show you what the hypothesis test looks like long before we talk about hypothesis testing, but I'll show you something we can use, and then we'll refer back to breaking this apart in a little while. We have what's called our null and alternate hypotheses. And our null hypotheses, we can test to say we have normal data. And then we have an alternate hypothesis that says we have non-normal data. And we're going to be dealing with confidence. We're going to talk about all of these things in a little bit. And then we're going to have an alpha, is what it's called, of 5%. And there's a number down here, this p-value. And you'll see that this is for what's called a normality test. So I can actually use this number, which again, isn't going to make much sense now, but we'll come back to this several times. But I'm just saying what's cool is I don't have to visually look. The p happens to be higher because 5% is, translates to 0.05. This p, the p value is higher than, let's put alpha for now. And what that means, before I teach all this in detail, the P is high, the null will fly. So all I'm showing you right now, minus forget all of that, I'm just showing you for now. In a couple of hours, we will reveal all that stuff laid out, and we'll pick that apart step by step. But what's cool is there's something on this document here that tells me, do I have normal data? I don't have to just look at it visually. I can look here and say, do I have normal data? Actually, I do. Same with this one. Do I have normal data? As a matter of fact, this is really represents a normal curve, like quite a bit, based on this p-value down here. Based on this p-value. All right. So let's step back a minute, get back on track before we dissect all of that. So first of all, what is our location? That is where we get the mean, median, or mode. And here we have our mean of 535, which means we're 400 above. So our location matters, because where is our location in relation to where we should be? Well, we should be centered between those specification limits. Should be at 135. We're at 535, or we're at 473. Okay, location, that's now shape. Do we have what's considered a bell shape, a normal distribution? So what is the shape of the data? Well, this one looks like it kind of tails off. I'll switch colors here. Kind of looks like it goes whoop and tails off, but apparently not quite enough, because that right there, if something is tailed off like that, that is called a right skew. And if it tails the other way, so if you would have seen it look like this, then you would have, well, I'll say that, you would have a left skew. Just think of the tail points to the right or left. But you can have skewed data. And if you have skewed data, don't sweat it. Does that mean that we can't do the test? No. If we had data that represent a skew, if our shape was not normal, then what we can do is, as black belts, we can actually run a different set of tests. That's it, but I have to know these things. So I just want to stress why your black belts are doing this with you. So I want you, as a teammate in green belt, the taxonomy you've got to know is, hey, listen, in descriptive statistics, what we've got to figure out is, what is the location of the data? What is that shape? Is that shape a normal distribution or not? And then the next one is the variation. So how do we figure out what our variation is? Now, there's a couple of concepts that we really need to talk about here for a bit first. So we have variation in our process, and we took a look at the variation. But in all reality, when we looked at that variation at this point, what did we see? If we had short-term variation for our short-term data, it was what, 56 for team B and 67 for team A. But in all reality, what does that even mean? How does that compare? Are those different from each other? Are those good? Are those bad? Well, how in the heck do we figure this out? Well, I'm going to step back for a moment. Let's cover the empirical rule. The empirical, actually, I'm sorry, I forgot one concept I want to tie up before we move on. So I'm going to hold off on the empirical rule. I want to talk about the central limit theorem. Wrong deck. So in the central limit theorem, I'm going to show you something that I have built in. Okay, so when we're looking at the central limit theorem, let's take a look at the data on the bottom and why this matters. When I said to you earlier today, so I just using a dice example, we said that a sample size with our continuous data, a sample size of 30, about 30 sample averages are going to get you what somewhat represents a normal distribution. And now what that means on this paper here, let's take a moment and let's draw this out so we can actually see it. So if I had a curve like this and we say, I'm going to roll, or what it means is let's say we run the sim 30 times and we have 30 sample averages. And by that, the data I'm talking about is saying we ran the sim, this is one run and we got 536 seconds. Okay, this is run 2 and we got 473 seconds. What it's saying is we collect those 30 data points, or I'm sorry, not 30 data points, however many data points we had. And we take the average from run one, and we say, let's say the average is like 600, right? And we take the average, and the first one is, 645, and then it's, 573. The next average that we have, the next one is going to be, 658, and on and on. So as we collect these data points, what it says is the sample averages over time are going to start to create what represents a normal distribution. If we keep collecting these samples, you're going to eventually, after about 30 data points, if I were to keep drawing 30 data points, you're going to have something that represents a normal distribution. So if we ran the sim 30 times and we got the sample average from each of those 30 times and you plotted them, you're going to end up with something most likely that represents a normal distribution. So that's using the sim, but let me show you using dice. It's kind of fun. If we rolled one die, just one die, and I roll that die 500 times, okay, 500 times, bam, bam. And I did this with a random number generator. So there are 500 rolls. You see there's dice one, and there's like 500 data points on here. So this is representing rolling the die 500 times. What would that look like? Well, generally speaking, if we rolled the one die, it would come out to be pretty even. Hold on. There we go. It would come out to look pretty even, right? Everything has the same option to be hit. Like if I roll a 1, 2, 3, 4, 5, or 6, you'd expect it to be pretty level, right? Because I have the same probability of rolling a 1, same as a 2, 3, 4, 5, and 6. So I rolled 500 times using a random number generator, and I get a histogram that looks like this. That's one die, 500 times. Now, what happens if we roll two dice 500 times? Because the concept behind central limit theorem is the larger the sample size and the faster you collect them, the quicker you're going to get something that represents the normal curve. So one die, meaning one simulation, right? Equivalent of just running the sim one and taking the average 500 times, it'd be like this. Now, dice-wise, let's say I take two die. Now I rolled two die 500 times each and took the average of roll 1, roll 2, roll 3. So I rolled two dice 500 times, not each side, 500 times, and I took the average. Well, look what starts to happen. That's two die. Now, what if I rolled three dice and I took the average 500 times? What about four dice? Finally, remember when I said about 3 to 5 is usually a good sample size? There's 3, 4, and here's 5. Look what happens if I roll 5 dice 500 times and take the average every time. Check that out. You end up with the normal distribution. And that right there is playing out the central limit theorem. Well, let's go into the empirical rule now, because that's going to become very important. But so now we're going to talk about what the empirical rule is, because this helps us to say, well, why does this normal distribution really matter? Not only does it dictate which kind of tests we can use, also watch the interpretation. The empirical rule is something you may have seen probably in about high school. Somebody put, yes, our kids used it during COVID. Absolutely, it's great. It's an amazing thing to use. Pen again. When we're looking at this piece of, because we're moving slightly into variation now. So let's take that normal curve when we're talking about location. Where's our center point in relation to where it should be? What's our shape? Do we have a normal distribution or not? Because in this class, we're going to be working with normal distributions. Black belt, we work non-normal distributions a lot. But in this class for green belt, most of what you do is going to be with the normal distribution. So that's what we really focus on here. So from here now, we're going to be working on this normal distribution. And what the heck does this thing mean? Okay, if we're going to use this variation, we're trying to figure out now how much variation in our process. What is that? What does this 67 mean? What does this 56 mean? That's what we're trying to describe at this point now. Well, let's take a look at the data and we say, check this out. Anything within plus or minus 1 standard deviation. And now, actually, let me go through the calculation first. So we're gonna walk our way through an example on the slides first, and then I'll take you back to the data. I think it'll make more sense that way. It always does. So before we get to that empirical rule, let's actually talk about variation. Like, how do we measure variation? Because at this point, we've talked about variation on day 1 and now and said, okay, it's between the upper and lower spec limits, and then our data set has this variation, our measurement systems has variation, but what does that all mean? How do you capture that? How do you make it relevant? How do you make it make sense? What the heck? You say the key to unlocking our success is reducing that variation. Well, we have to have the understanding of what variation really is and where it comes from now. This is the one area, I'll tell you, for about the next 30 minutes, this is the only formula outside of that little y equals f of x that I really want you to pay attention to. Not memorize, not worried about that, but understand just what goes into it. Because this is the crux of Six Sigma, meaning you'll see when I'm at the end of this, when I finally tie all this together, that this right here, when I said it take me a few hours to define Six Sigma, I'm about to do that for you. Well, first it starts with this. Every data point we have deviates from the mean. Everything starts with a mean. Every data set is described, or in the normal distribution, there is a mean and a standard deviation. We know what the mean is now, or the central tendency. We know what that is. Let's talk about that standard deviation. So there's a center point, and I'm gonna use flat, easy numbers here for the data, and I'll try to be as close as I can. And that's simply because doing math in public is extremely difficult. So I think we had 473 and like 500 and something. So I'm going to say collectively we have an average. I want you to get used to this because sample average is marked by X with a bar over the top. So our average is 500, we'll say, for our data. And when I'm talking about our data, I mean, we took all of our data points and the average is 500. Well, here's the thing. I'll use a number closer. What the heck? Let's pick on A. A's is 535 and then 67. So what I'm going to do, 535 and 67. So the numbers I'm going to use for math in public, I was right. I'm going to use 500 and I'm going to use, I'll round up for it, 70. Okay, so does everybody understand, like, me using those numbers? Like, I'm doing it because I have to do quick math in my head. Are we okay with that? Okay, thank you. So if you're learning, like, why did you use 500? I used it because I have to do math and it's really tough to do otherwise. So I'm gonna say, all right, cool. So our average is 500 seconds for this class, we'll say. And then if you noticed, just about none of our data points actually hit 500, okay? Let's toggle. Take a look here. Oh, geez, there actually was one. That's a good example then. So I'm saying we're using 500. Well, check this out. We got 581, 615, 678, 728. So 622 is not 500. 668 is not 500. 501 is not even 500. 390 is not 500. And that's important for when I do this drawing here, because if we have 500 that we're using, our average, if we're going to use 500, well, each of our data points that is not exactly 500. Remember, there was one that was 500, right? That's cool. Well, that one's right on the line, okay? But every other data point is not on that line. What that means is they all deviate from the mean. So each of those data points individually deviates from the mean. So deviation, pretty simple concept to think. So let's say we got something like, on top you got 503, 502, right? We saw these, and you got 498 below, and you got 497 below. So what you'd see is they all deviate from the mean above and below. Now, logic-wise, I do want an answer from the class here. Since the mean cuts the data in half, If I were to add up all these deviations from the plus side and the minus side, what would I get?
Should be 500.
Well, that would be the average. Good guess. Very good guess. But if I added up, let's just do an example. Okay, so we got the ones we see: +2, +3,
Oh,
-2.
yeah, it should be 0.
Yep, comes up.
This
Whoa,
should 0 out.
perfect. For your logic, by the way. But so if I add those up, you're at 0. And now you're going to go, okay, well, why did you show us that? That was kind of dumb. I'm going to show you because this is a 3-step process for us understanding variation. So we look at this and we say, okay, if we added up the top and bottom, I'd end up with 0. Is there anybody that doesn't see that? Again, I'll pause there, concept by concept. Okay, Evelyn, thank you. Getting some thumbs up. Now, since that's kind of worthless and I come up with 0, that's something I really can't use that. That's not very helpful. Okay, so step 1, though, we look at those deviations. We start to assess them. Then step 2. Step 2 is we take those deviations. And now how we get to these and how far we figured out is how far above the mean. So you have your mean right here. This is your mean. That's why I said it's kind of important for you to understand the X bar and all these things. I'll try to write out the labels whenever possible. It says we're going to take each point, and we're going to minus it from the mean. That's it. That's how we get the deviation. Everybody sees that pretty clearly. So that is not an intimidating formula. It's just simply, all right, take the data point, subtract it from the mean, every single one of them. Well, crud, the answer is 0 at the end if you just added them all up. But we got to do something with that now. What we're going to do, this gets a little bit more intimidating, but it's okay if you follow, if you just slowly follow. If you look at this right here, this is what we just did. So this is each data point we just saw. Trust me, it'll help if I write it all out for you. And this is minus the mean. And then what it says is we're going to square each of those. So we're going to take each of those deviations and square them. So of deviation from the screen before, squared. Now this part over here is just simply saying we're going to sum all the deviations squared. So we square the deviations and it gets rid of those negative signs, right? If you take -3 and square it, it's 9. -2 and square it, it's 4. Right? So now we have something. Seems kind of weird, but we'll talk about why it makes sense in a minute. So all this is saying is we're going to sum all of our squared deviations, and we're going to divide that by our sample size minus 1. So to rewrite it clearly and neatly, all this formula is saying is sum all my squared deviations and divide by, it's called my degrees of freedom, but sample size minus 1. So very simply put, I'm going to take a look at how far each of those are from the mean and square them. Again, a concept that you guys all get, nice and easy. And then I'm just going to add, all of this one to this one, to this one, this one, this one, this one, this one. So I'm going to square them up and add them all up. And then I'm just going to divide by my sample size minus 1. And that is the formula for variance. Now we're getting closer here. I'm going to pause. Let me pause for a moment. How are we feeling? All right, I got a couple more now. So now what happens is we're in our variation. But just like deviation, we're kind of leaving ourselves short at this point because there's something missing here. Now we have a number. Let's say we add up all these squared deviations and we get 100. Let's just say we add up all those squared deviations, divide it by n minus 1, and we end up with 100. Okay, cool. But there's something wrong here. What happened to the units when I just squared everything? I'm actually dealing right now with seconds squared. Does anybody know what a second squared is? If you can answer that, please. Yeah, I mean, I'm all for it. but I have no idea what a second squared is. That's not something that makes sense and is usable to us. That's why I said it's a three-step process. So this gives you your variance. So we had our deviation that led into our variance. And if you notice, the formula just built on itself. Well, guess what we're going to do to get our standard deviation, the final step? This should not be intimidating because this is your variance in here. This whole thing was what we just did. This is simply the square root of my variance, which before we said we got 100 seconds squared. Again, I made that up so I can use numbers. So what's my standard deviation then? Square root of 100 is 10. I'm going to let that one go because I got a few answers of 100 seconds. When you take the square root of 10, do we remember those? Hopefully it was just like, oh yeah, dude, I remember that. Everybody cool now?
So are you considering seconds a variable then?
I think you might be overthinking it. Right now, I'm just, okay, I'm gonna step back a second. Let's walk through this just real quick. And maybe this will make sense. Because literally I'm just talking about the square root of something. Like you guys remembered that when I squared something, for instance, if I square 3, I get 9. Well, then what's the square root of 9? And if I reverse that, it's 3. If I square 2, I get 4. So what's the square root of 4? 2.
No, I think you're right. Just was overthinking it.
You were. I mean, I know because you guys. There's a couple of you in here that have a background in this, and I can clearly tell. And I'm using very simplified examples. Don't the square root and the square cancel each other? Yeah, I know it's a pain in the butt. I'll go through that at a later time on that one. I always hated that too. Why they square these and then take the square root. It's a huge pain in the rear. But what happens though is, again, we took the deviations, just simply took each data point minus the mean. Okay, so how far are they from the mean? Then we squared each of those deviations and we added them all up above the 500, above the mean and below the mean. We added all that up and divided by n minus 1. But when we did that though, because we squared each of the deviations, we ended up with 100 seconds squared, which isn't really usable considering it's seconds squared. I don't really, that doesn't make much sense. If I had dollars squared, it doesn't make much sense. I'd like to earn dollars squared, but it doesn't make sense though. So dollars squared, time squared, right? So what we do then is just simply take the square root of it to get to our standard deviation. Take the square root of that variance you got and you get 10 seconds squared. 10 seconds, oof, sorry.
Yeah, so really it should just be 10.
I think you cut out.
Yeah.
I'm sorry, go ahead.
Yeah, so the squared refers to the unit, or excuse me, refers to the number, and then the unit is ancillary.
Yep.
I think that's where we were getting.
Yeah, it's a number, and the number and the unit were both squared at that point. Yep, I think you just overthought it, no problem. But is everybody good now? We take the square root. Okay, I got one thumbs up. I want to make a couple more because we got folks that are. Okay, all right, seeing a few thumbs up. Good. Actually, quite a few now. Okay, so now what's going to happen though? We finally now for standard deviation, we came up with 10 seconds. Now, remember for you guys, you had like 57 seconds and whatever the other one was too. You had I'm using this for quick math in here, but now we're going to talk about what does that mean? If I have 10 seconds as a standard deviation, and we're about to take off from here. So if I had 10 seconds, or in your case, if I had 67 seconds, 56 seconds, what does it mean? We need to put some context behind this. So what happens now is we are going to use the example. I'm going to create a couple of extra ones here. We are now going to use the example that we just pulled from the class. Now, it's not your real data because I can't add that math that fast enough. We have an average. Whoa. It's not what I want to do. We are going to have an average of 500. And we now had determined that we have a standard deviation of 10. Okay, now it's 12:54, so we're going to take a break for a moment. I like to really make sure we're on the hour for stats so we can kind of settle back and just take our time. So after the break, we're going to tie this concept together and say, okay, we see what this, the standard deviation is calculated. Now, what the heck does that even mean? We know that you're saying that this is the calculation that tells us how much variation we have, but now we need to take it into a practical sense. All right, so what's going to happen? We'll take a 10-minute break. Do I have any questions right now before we go on a break? All right, I'll see you guys in 10 minutes. Take a nice brain break. Okay, back to it. Now, when I said that we were going to get to the point where we need to start talking about this in practical terms, I understand that as we go through the formula, things can get a little bit confusing. I totally understand that. It's that way with any formula in any like math class ever, right? So now let's get to the practical side of things. We've come up with these numbers, and in our example here that we created together, we have an average of 500 seconds for our center point, and we have a standard deviation of 10 seconds. Okay, so let's just say historically, this is the average, and this is what we're trying to accomplish. Or I mean, this is what we currently have, I'm sorry, with this data set. Now, if the average is 500 seconds, let's write that down. What it's saying is that if I go plus or minus 1 standard deviation, that is going to be plus 10 and minus 10. So I'm at 510, 520, 530, 540, 550, and 560. Just like on the other side, if the standard deviation is 10, it's going to be 490, 480. I'm going to mark it out like this: 70, 60, 50, and 40. Okay, so that's plus and minus. That's using 10 seconds as a standard deviation. And when we're looking at this, called the empirical rule. But more importantly is, what does it do? How does this perform some sort of function? What are we going to do with this? What this tells me here is, if I'm plus or minus 1 standard deviation, here, it tells me that I would expect, with a standard deviation of 10, I would expect, if we were to run this sim again right now, if this was our data, it's our historical data, we'll say it's got 100 data points and all that stuff. We go run the sim again today. I would say that 68% of my data, I would expect to fall between 490 and 510. Now, we set that out a little bit, or go out to 2 standard deviations, and I would say then 95% of my data, I would expect to fall between 480 and 520. And now let's get out to the 99. Is 99 good enough? Plus or minus 3 standard deviations. I would expect 470 to 530. Somewhere between 470 and 530, I would expect 99.7% of my data to fall there. If I ran this, 20 more times today, and we ran it and we collected the data, we took an average of, every 30, a group of 30 goes through and we take an average, another group of 30 goes through, we take an average. I would expect 99.7% of that data to fall within 470 to 530. That's what the empirical rule helps us to see here. And if we're talking 6 sigma, you're talking all the way 440 to 560. So if I were to have a 6 sigma, like if you're talking about getting all out to 6 sigma plus and 6 sigma minus, we're talking 440 to 560. Now, what does that mean? That means that that's the spread of my data, but in itself, it doesn't mean anything. That's just laying out the empirical rule, looking at it going, okay, 6 sigma would put me between 440 and 560, but that has no relevance until I do something very important, which is it has to go between my upper and lower specification limits, right? It does. Well, if I were to draw my specification limits on here, where would they fall? Heck, they're over here, right? My lower spec limit of 90, my upper spec limit of 180. So when we say that, when we're looking at this variation, we have an allowed variation, allowed, we remember, allowed of this 90 seconds in between here, right? This is the allowed variation, 90 seconds. But yet, if we were to, what's the distance between 440 and 560? 120, right? So would we be able to fit all 6 sigmas between the upper and lower spec limit? This is where it gets really important, where I really need feedback. Could I fit all those specification limits in there? Let's do another one, or another look at it. So I got 90 seconds, and I got 180. If I were to move this data set, or move this over, would all 6 sigma above and below the mean fit in there? Would it look like that? No. Why? Okay, theoretically, or not theoretically, like practically speaking, I need an actual verbal explanation here. What's kind of telling me that that there's too much variation in the process?
Because the process right now is not lean enough. So it's not allowing us to get within those parameters.
So let's say the lean and Six Sigma, yes. Yeah, I mean, you're absolutely, I totally understand what you're saying. Yes, there's too much variation. We have a variation of 10 seconds in this example. Could we fit all 6 sigma above the mean and all 6 sigma below the mean in those specification limits? And the answer is no. Now, why does that become important, especially for explaining what 6 sigma is? Here's a little fun fact for you. This is where it gets really fun, I think, anyway. So when you're talking about 6 sigma, what the heck is 6 sigma? First of all, what is lean 6 sigma? Lean, we know now, 6 sigma. Sigma is Greek. Very important. I don't get too nerdy on you. For, guess what? What do you think it's Greek for in the English? Standard deviation, what you just calculated. So when we say what is 6 sigma, first of all, sigma means standard deviation in Greek, or Greek is sigma is the word for standard deviation. Now 6 sigma, what it means for all practical purposes is that our goal is to get all 6 sigma, 1, 2, 3, 4, 5, 6. Well, let me squeeze it. All 6 sigmas above the mean and all 6 sigma below the mean to fit between those specification limits. So what is lean 6 sigma? We remove waste to the process and remove variation to the process where we can get 6 standard deviations above the mean, 6 standard deviations below the mean within those upper and lower spec limits. Practically speaking, what does that mean? I am 99.9997% defect free. That's what 6 sigma stands for. The name of the class, if you were to do it in English, would be lean 6 standard deviations. So going back to our data, let's put this in real terms now. Okay, we have 90 seconds. I'm going to use your data. I've been doing a lot for A, so I'll do this for B. Somebody has to get a calculator and get ready. I need this because I'm going to put this in real practical terms right now. So this is going to definitely take me asking for somebody to add some math for me. So team B, let's use your stuff. We have 56 is our standard deviation. And so 473, 56, 473, 56. I'll write that down here, 473, 56. So this is real data for what your stuff actually is. So our mean is 473, a standard deviation equals 56-ish, right? Standard deviation. Now, that means we're at 473. I'm going to draw this a little bit bigger here. So I actually have room. Do I have a plain one? I do actually have a plain one. Sorry. I should have just used this one. 476. Was that it? I'm sorry. Oh, 473 and 56. Sorry, 473 and 56. 473 and 56. Standard deviation. And this is our average. And this is team B. So this is real data, real time. We're going to look what the heck this means for you all. If our center is 473, what is +1 standard deviation?
529.
529. And then what about adding 56 more?
585.
585. What's add 56 more?
641,
641. Next for 4,
697,
697. Okay,
753,
753,
809,
809. Okay, let's do the minus. 473 minus 56.
417,
417. Next,
361,
361. Next,
305,
305,
249,
249. Okay, next,
193,
193. I don't know why it's dragging like, wow, that was weird. I think it's because my wrist is touching. Go ahead. Next,
137.
137. Okay, so what this is telling me, real data, let's put it into real context for Team B here. Real context. If we were to run it again as Team B, you're going to go run it again this afternoon. If I'm between plus or minus 1 standard deviation, how much does that represent? 68%. So what I would say is this, I would expect this afternoon for you to run the sim again and your average be somewhere between 417 and 529. I'd rather expect 68% to fall in that tight of it, in that tight. Okay. What about if we go out to 95? I'll kind of do it up a little bit different for 2 standard deviations. So 95%, I would expect the data to fall between what, 361 and 585. And then I'll go out to 3, which is 99.7. 99.7. I would expect to fall between 305 to, what is it? 641. Okay, that's real. We'll stop at 3 right there for a minute. And then all the way out to 6 sigma. I would expect 99.9997% to fall between 137 and 809. Do you see a problem with this if you're talking to your boss?
The variation's too large.
You're talking right here about 3/4 of a day to, can somebody do 809 divided by 180?
4.5, roughly.
Okay, so let's see if this would be an issue. We're supposed to get between half a day to 1 day. That's our specification limits. That's what we're told. But yet, if we were to do a 6 sigma process, and like that's what we'll say we're going for here, right now, I would tell my boss for current baseline data that we've collected, well, 99.9997% of the data should fall between 3/4 of a day and 4.5 days. What do you think the reaction's going to be?
Unacceptable.
You better get to stepping. I'll tell you what, that ain't good, friends. That ain't good. So let's take a look at essentially what it should be. Okay, right now we have a standard deviation. Again, remember it's 56. Let's take a look at what it should be. 135 is a center point. Like if we were, remember, if we were to do the 90 to 180, 90 to 180. Now I think it's somewhere like 7. If you did like a standard deviation of 7, that is what, 142, 149. Wow, sorry, 149, 156, 163, 170, and 179, I think, ish. Okay. And then down here, you've got what, 128, 128, 121, 114, 107, 100, and was it like 93 or something like that? So you're talking approximate. So in order for you to be at a 6 sigma, like getting all 6 sigma, all the 6 sigma above the mean and 6 sigmas below the mean, you have to reduce your variation. So you have to have a mean of about 135, right? That's the center point. And a standard deviation of about 7. So a standard deviation of about 7 seconds. So this is what right would look like. This is right. 135 centered, and then about a 7-second standard deviation. And that would lead you to all 6 sigmas above the mean and 6 sigmas below the mean to fall within the upper and lower spec limits. And that is Six Sigma. Does everybody see the connection when I took it from real data then to what right looks like? Here's right. Right now, you're at 3/4 of a day to 4.5 days, but yet we're supposed to be at half a day to 1 day. That's how tight we're supposed to get it. Half day to 1 day. That's the allowed variation. And right now, we're at 3/4 of a day to 4.5 days. Does that help to clarify it a little bit when we're trying to quantify when we're off? Very much. Okay, cool. That's what I'm hoping to see, because sometimes when I draw what right looks like using real data, so I try to do one example where I'm using round numbers, right? And then I try to use real data from one of the two teams and then try to show you what right looks like. And by that third one, a lot of folks who aren't really comfortable with the concepts are just like, okay, now I get it. Because now I know what we're shooting for. We should be at, 7 seconds, but yet we're at 56. I mean, that's a reduction of, quite a bit. I don't even know what percentage reduction, probably 80, 90%, 80%, something like that, 85. I don't know, I'm just going off the top of my head.
Greater than 1.
So it's a big deal, and we're way off. So again, I'm going real slow here on purpose and kind of just giving you guys time to think about this, because this concept, we've spent basically, it took Monday, Tuesday, and Wednesday collectively to even get to the definition of Six Sigma. And Six Sigma stands for, sigma is standard deviation. It's a Greek word for standard deviation. And it's saying 6 sigmas above the mean and 6 sigma below the mean, all within our specification limits, which equates to, at the end of the day, with all of it, in terms that really matter, 99.9997% defect free when you're dealing with defects. And then in this case right here, this is saying, I would expect, I can tell you predictably wise, when we say predictable and consistent. So when we're looking for a predictable and consistent process, this process is predictable and this process is consistent, because I can tell you 99.9997% of my data, the next average I pull, if we ran the sim next week, 99.9997%, I would expect could fall between 93 and 179. That is a predictable process. And that is what we're trying to get at with variation. So I'm going to take a pause and just kind of, like I said, I'm just not like an awkward pause here, but just making sure that, there's no questions that pop up, because now we're about to get really practical and we're going to get into hypothesis testing and stuff. So this is becoming very important, because we're wrapping up the descriptive portion. And then we're going to start using this data to make inferences. She'll get us going here. Let me make another couple of copies of these before I forget. And again, I throw this in at the end of the day for you. I used to hand draw all these during class, and let me tell you, trying to draw a straight line on the screen is not easy. So finally got smart enough to make this ahead. Let us go back. We'll back up. And so what we looked at, remember, in summary for descriptive statistics, we talked about location, meaning where is our data centered? And where is it? And it matters because where is it centered in relation to where it should be? Then we talked about shape. Do we have that normal distribution? And the central limit theorem, we talked about that, how to, the larger the samples and the closer they are together, we're going to get that, sample average size. If we use about 30 sample averages, thinking that dies, using 5 die, it's going to get us to something that represents that normal distribution. And then we talked about variation, which is really the mother lode here. I mean, that's what Six Sigma is all about. It's a war on variation. So all that was to build up to the point of saying, how do we capture our variation and make sense of it? Well, the computer is going to do all the hard work for you. Okay, it's going to take that. It's going to take the data you put in. I mean, you just put this data into it, right? All we did was take this data into and put it in there, and it came back and said, well, here's your standard deviation. For short-term data, here's your standard deviation. So then it did that for you. But now the hard part, though, or not the easier part, I'm sorry, once you get it down, is to say, well, what in the world does that 56 mean? Well, it means something in relation to these specification limits, because I want this number so small that I can fit 6 standard deviations above the mean and 6 standard deviations below the mean, all within those spec limits. Taking this thing here, not only leaning it out and centering it, getting that time down, but also getting to that more predictable and consistent process. So centering my normal distribution in between the spec limits. Location, shape, and variation. Here we go, next part of it. We are now going to get into inferential statistics for a little bit. Now, inferential statistics help us to make inferences, right? I'm using the data that I have because I only have a sample. So let's say you're working with somebody like Accenture, for instance. Accenture is a big company, and Accenture last year, I think I already told you, they onboarded like 120,000 new people across 56 countries. We're going to have all 120,000 data points and all the stuff that we need on them? Probably not. Do we need all of them? Probably not. What we need is a sample of them, a representative sample that we can use so we can make inferences about the population. So we need a sample that represents the population so that we can make inferences about the population. And so with hypothesis testing, this is where we get into our null and our alternate hypotheses. This is going back to our 5th grade science classes when we used to, have little Bunsen burners and say, hey, what do we predict is going to happen? If I light this on fire, it'll explode or it won't, right? We ran experiments. This is using our scientific method here. So let's draw out a hypothesis before we even get into the words, because the words can be somewhat confusing. That's why I like to start with this, drawing it out together first. Let's take a look at something like, let's grab one of these here. I'm going to stretch it out a little bit. We're going to draw a null and an alternate hypothesis. So when you're doing your null hypothesis is the status quo. It's the something that says there's no change, there's no significant difference. So let's use something that'll really make sense. For instance, the null hypothesis, we'll say for one of these, is that the average for team A, equals the average for team B. And when I'm talking about the averages, let's just be clear here. Let's compare these. And we've got 473 and we have 536. And you go, Luke, come on, man, they're different. You don't know that, actually. We don't quite know that. So let's start out with our null hypothesis. It says there's no changes to status quo. Any difference that we observe between those two numbers? Actually, I'm going to write those down. Should have done that ahead of time, sorry. 473, 536, 473, 536, 473, 536. So it says, hey, listen, the sample average from team A is the same as the sample average from team B. The only difference is sampling error, noise, right? It's just, there is no statistical significance between the two. Our alternate, though, is called our experimental hypothesis. This is the one that we're going, hey, listen, I want to know, is the sample average from team A, is it greater than the average for team B? So that's our experimental hypothesis. And you could also write this in other ways as well. So it could be, or is the sample average from A just simply not equal to the sample average from B? That's another way you could write it. Or, oh my gosh, where are we going with this? Or the sample average from A is less than sample average from B. I can write any test that way. I got 3 choices. It's either not equal to, it's less than, or it's greater than. Okay, so I have 3 options. It's just, and then I'll show you how little it truly matters. If you're like, well, crud, I flipped the signs, or I think I asked the wrong question. I'll show you how fast it is in the statistical software just to simply fix your error real quick. So don't get too hung up on those. We'll talk about them as we move forward, but not that big of a deal. But what these are actually different because these are actually talking about the tails. I'll get to the tails here in a moment. But right now, just for the null and alternate hypothesis, what we want to say is, all right, our null hypothesis here, this is assumed to be true unless you provide enough evidence in your experiment that it's not. Let's put that in terms we use in the American Justice Society. That null is innocent until proven guilty. And prove is the wrong word in statistics, but that's how it works in the legal system. You don't prove anything. I want to make that clear. You don't prove a thing. You can only provide evidence for something in statistics. All right, so let's take a look. Now that we've drawn it out a little bit, let's take a look at the actual words that are in the slides. So if you're looking at your null hypothesis, it says it assumes that any difference between that 473 and 536 is just chance. It's due to chance. Team A may have very well had a lower one next time and B higher and all that, right? It's just chance. There's no real difference. Number two, it proposes there's no statistical significance. They are different, but it's not significant. And it attempts to show that there's really no variation between those variables. Bottom one, it is presumed true until statistical evidence nullifies it. That is a null hypothesis. And we will work on these. I will write so many of them in front of you over and over. I handwrite them all class so that we get used to them. Next, so is the alternate hypothesis. The alternate hypothesis, says that there is an observed difference between the two. Usually the goal is to reject that null hypothesis, right? If we're running an experiment, we'd like to reject the null and say, hey, there's evidence here that the experiment worked, or there is some sort of observed difference. And then data is collected to see if we can reject the null. Now, something that's important is there's only two options you have in statistics. So we got to get used to this funny language. You can either reject the null, or fail to reject the null. Those are and I know it's funny wording, but those are the two words that are used in statistics. I either reject the null, and then so let's go back over here and I'll tell you what those mean. Let's put it in practical sense as we're walking through. If I reject the null and I go reject that null, I'm saying there is evidence that team A has a higher average than team B. It is statistically significant if I reject the null. Now, if I fail to reject the null, what I'm saying, there wasn't enough evidence provided that they're actually different. 536, 476, or whatever the numbers are, kind of forgot already. But 473 and 536, there is no statistical significance. They're not statistically different from one another. So I can either reject the null or fail to reject the null. We want to stay away from words like I accept the null. I accept the alternate. The alternate's true. The null is true. They aren't true. We just don't have evidence for them. Remember, you're dealing with a sample. When you're dealing with a sample, we don't know the truth. We actually don't know the truth. There is always going to be an error in there that we could be wrong. That is possible. And we'll talk about that in just a second. There is a possibility. And when you have that possibility, that's when we say, well, how confident do we need to be? Generally, in most tests, you're going to need to be 95% confidence, which means confidence, which means that the other 5% there, this is called your alpha, which means I could be wrong. So there's a 5, you're saying, all right, I'm going to set my confidence. And now let's take the look at that confidence here briefly and step back for this null and alternate hypothesis. And let's use our real data, because we'll talk about a confidence interval, for instance. We'll talk about a confidence interval and then confidence as it relates to this, because there's two pieces of confidence we need to talk about. So if I'm going to take my data, let's take a look at report A. Let's look at our data for A. There we go, histograms and descriptive statistics. So we're going to look at the lead time here with 95% confidence. Now for team A, this one's a confidence interval. I'm using confidence in two kind of different ways here. But let's take a look at team A's data. And this brings me to a point also of what's called a point estimate. So point estimate. And the reason I say that is because this particular sample that we collected is a point in time. This is only one data point. This is only one set of, we have 38 data points, but this is only one set of data. So this is a point estimate, meaning if somebody were to ask me, or the boss asks me, what is the average time for our process? We would think we're going to jump to, well, it's 536. That's the average. Is it? No. This is only a sample. There's actually a range of numbers that it could be. Remember when we found 68%, it could fall here, 95, it could fall here. Well, let's talk about that 95 now. This is taking what we learned already with that 95 and saying, okay, the confidence interval for the mean, 498 to 570. Take a look, is that what 498 to 573? Oh, we're off a little bit from rounding and all that crap. But if we're taking a look at, oh, we were looking at the other data, sorry. Yeah. So 498 to 573. So what this is telling me is that I'm 95% confident, or I'm sorry, if I were to do this 100 times, 95 of them would fall between 498 to 573. So if I'm going to take a look at these numbers here, I'm going to say I'm 95% confident that my population average, not sample, we're dealing with the sample. I'm 95% confident that my population average is going to fall between 498 and 573. Because remember, this data set here is only one set. It's a point in time. It's called a point estimate. So there is a difference when we have a confidence interval. Hey, listen, 95% confident, my true mean falls somewhere in here. It's not necessarily 535. That's this point estimate. But it's somewhere between 498 and 573. That's a confidence interval. So you're seeing 95% is going to come out a few different ways and a few different times. Just like with, I think that was A. Yep, and let me use B. So if we have B, take a look at our lead time, 95% confidence. And so for team B, we're looking at the mean's not actually 473.38 for the population. That's for the point estimate. For this set here, we're saying the true population mean should fall between 406 to 540. Somewhere in there, 95% confident, my true population mean falls within there. And you say, well, what about that other 5%? Like you keep saying I'm 95% confident that it falls between that zone. So 95% it falls within that zone. Well, what about this other 5%? Remember, when I'm dealing with a sample here, it's possible that it doesn't fall within that 406 to 540. It's possible that it actually doesn't. I have to assume some sort of risk in this. So all right, so I have to assume some sort of risk, which takes me back to that alpha that I was showing you a few minutes ago. When we were talking about this alpha, this 5%, I'm saying, listen, I could be wrong. No matter what the data comes out to be, because this is a sample and because I'm making inferences, there's a risk I could be wrong. So in that case, I have to accept and set some sort of number, like what type of risk am I willing to accept that I could be wrong? And 95%, I'll show you later in the presentation that it's not an arbitrary number. That's considered for a normal process. So in almost everything you do, you're going to be using 95% confidence. So you can get very used to it. And stats books are going to be built around 95% confidence. And so are examples you see online and stuff. But just understand, it can be 99% confident. It could be 90%. But 95 is pretty typical. And so you'll see us using that quite a bit in here because that's what you're most often or most likely to see and use when you're practicing, when you're a practitioner. So I could be wrong that I make a wrong inference. Now let's put this together here because there's still a little fuzzy. Even for me, it's a little fuzzy. So let's take a look at an example. We're going to actually use a non-statistical example here. Well, after we do our steps. So we have 10 steps. We have 10 steps that we have here. So the steps that we use for these 9 steps for hypothesis testing are as follows here. When we're setting up a hypothesis test, the first thing we want to do always, and I can't stress this enough without, kind of sound like all crazy if I'm like, never, 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 never is double negative, not do this. Always, always do it. Because one of the things we find out as you progress and you're in black belt, master black belt, people forget what the heck they're testing and what it is they're going for more often than you think. It happens a lot. So define the problem to be studied. What are we studying here? We're studying lead times for onboarding, right? We're studying lead times for onboarding. Great. What's the objective? Okay, determine which team is better. So we're looking at lead times. So the problem that we're studying here is that both teams are too slow, but we're going to see which one has a better current process. Cool. Specify the null hypothesis. Null hypothesis, if you remember, that's considered status quo, right? No change, no statistical significance. So we say the average for team A equals the average for team B. The next one is we do our alternate. And the alternate can be written HA or H1. You'll see that you'll see those between different books and presentations and everything. Whichever, it's fine. As long as the null hypothesis just says H naught or that 0 on there, whether you're using H1 or HA, it doesn't really matter. I just use A because it stands for alternate in my mind. And the alternate hypothesis, the question we could be asking is there a statistical difference between team A and team B? That's our null and our alternate hypotheses. So right there, this right here, I'm hoping you can see now that this is very, very clear. What we're studying in these first few steps says, okay, this is what we're experimenting for. We're going to see if these two are similar. Actually, I used the word better, so I should have actually, let me delete this thing real quick because the way I phrased the question will throw you off. Okay, I actually asked if team B is better, essentially. So I'll say, is team A greater than team B? Because it actually was higher. So we'll say, is it better than team B? Or is team B better than A? Cool. Okay, practical significance, we focus on a little bit more in black belt, but for at the green belt level for practical significance, when you're talking to your subject matter experts and you're working through this, you say, listen, there might be a difference and I'll use a different example here. If we are working on the actual project itself, and let's say we're seeing if we made any significant changes. Okay, we're going to say team A before changes equals team A after changes. The alternate would be team A before changes is team A would be greater than team A after changes. Okay, I'm going to pause for a second because what I'm saying here, this is like essentially in this class or what you're doing on any project, this is actually the hypothesis you'd be going for right here. And it's simply stating that before changes, we haven't made any changes yet, and we have an average. So if we make these changes, there's no real significant change. So when we test this late Thursday, it's yep, no change. Ideally, because remember, that one's innocent till proven guilty, or you provide evidence for it. Remember, there you can't prove something, but you provide evidence that says, okay, we made changes, and now our time before is greater, which is great, means our time went down. The changes we made took the time down. Perfect, that's what we were looking for. So this is actually the big one that you're after. And the reason I say this for practical significance is I'll give you a quick example. Beforehand, we were trying to remember. I need you guys to help me with
744.
No, I'm saying the mean for everything. Oh, I could have just gone here.
A was 473 with a deviation of 56.
We got 530, 535, or 536 here. for A, so 536. So what it says is 536 was our average when team A started. The other one was 476 for B. So what it's saying is, hey, listen, if team A, which is what we're focusing on here, it says this average of 536, let's say we pull an average afterwards, we run it, we got new process in place, and we pull a number that says 360, for instance. Okay, cool. So I can already tell you without running the data or having to do any testing on this, do you think there'd be a statistically significant difference between 536 and 360? Do you think they're just random chance that they're different, or you really think that'd be pretty significant?
They're not different.
They would be different. That's like almost 200 seconds apart.
You're still way outside the
Now,
you're still 200% above the goal, right? And so it's not necessary. It doesn't matter that it's better because it's not where you need to be.
So what you just did is you finished my statement, which is excellent. Right here, this will be statistically significant. This is enough where the computer would tell me this is significant. Well done. Great job, folks. However, practical significance is different. Practical significance says we set this as a parameter, with our team beforehand, and it says, well, we're not going to really negotiate anything other than that, 180 mark there. So if you're not getting down to 180, you're not going to hit practical significance. We'll just say that, for instance. And like you just said, doesn't matter. We're still at 2 days instead of 1. Is it statistically significant? Check. Computer will tell you yes. Is that practically significant? Nope. They are different. So does it actually have a real impact in the workplace? So this one is not computer related. This one is not formula related necessarily. With your subject matter experts, your teams, your leaders, you agree on. Maybe in the real world, since it's such a big difference, getting down to that 180, maybe we set it at like the practical significance. Practical is if you get down, if we can drop by 200 seconds. Awesome, awesome, awesome. Well, we'll say if we can drop by 250 seconds. Well, that's wonderful. Problem is we only drop by about 100 seconds. So again, it's not practically significant, but it's statistically significant. I'm not going to worry so much about that at Greenbelt, but I just want you to be aware of what that is. That takes a lot of subject matter expertise and stuff like that. So we focus a little bit more on that one in Black Belt there, but I just want you to know what it is. So I don't really worry about this one today, meaning like you guys setting this one, but I like to show you what it is. Now, for statistical significance at this point, we have to set our alpha. So let's set our alpha. And our alpha, you'll go with your confidence in your alpha. You say it's 95% confidence. And your alpha, which kind of looks like, is a symbol looks like that, well, that's 5% or 0.05. And that's what we're going to set that alpha risk. We worry about beta. Again, there's some black belt things we go on. I'm not going to worry about power and beta and all that stuff right now. So we set, and I'll show you why. Just trust me, after the non-statistical example, I will show you why. So we set our alpha and we set our confidence, or I'm sorry, because our alpha is there, that's what our confidence is. And then we're going to look at, well, how many samples do we need? And then we're going to look at, all right, what does the computer tell us? And then we're going to say what that significance level is. And I'm blowing over those because those are going to come up in a bit. But the idea that I'm trying to get to you for across at this moment in time is there is, for this scientific method that we have, there is a structure to how we lay this out. It's very important for us to define what it is we're actually studying. And we want to get that null and alternate hypothesis set up, see what it, get our result, or how are we going to interpret? That's where like it's in the alpha. And the alpha, remember, I'm using very loose terms, but if I'm 95% confident, remember, there is a chance that I could be wrong. That's why we don't say that it's true. And this is still fuzzy. So what's going to happen is I'm going to walk you through a non-statistical example, and then we'll take another break after that. Okay, so we set our alpha, we do all that stuff. Let's take this into something that can make sense because things are fuzzy right now. I expect them to be, and that's okay. But let's take a look if we're going to actually use a criminal trial. In the American justice system, remember, we're innocent until proven guilty. And again, I don't like the word proven, but works for this. So what happens during a trial? The suspect, or whatever you call it, they go onto the stand, and the lawyers then present evidence. And so we're trying to provide evidence for their guilt or that they're not guilty. So let's actually take a look at this. First thing is they come into trial, and you have your hypotheses. And what are your hypotheses? Well, your null is that they're innocent. The alternates, they're guilty. Pretty simple. We set our confidence, and we say, well, how confident do we want to be? And when I said this isn't arbitrary, in a normal case, we'll say this is, they robbed a convenience store with no weapons. They just did a smash and grab, and they were busted, and they're looking at they're looking at time spent, but maybe an ankle bracelet on them for the next month. Maybe we set it at 95% confident, and then, the alpha at 0.05. Well, what if this is a murder trial where their life is on the line? Probably a lot more confident, right? Maybe you want to accept the fact that you could be wrong by a lot less. Maybe we're at 99.99% confidence, and which means we have an alpha of 0.001. Really low. And you say, well, wait a minute. If you're talking about, they're up there for a capital punishment. I forget what that's called. Anyway, I watch Investigation Discovery all the time. I can't think of it. No worries. But the whole point is, somebody's going to say, well, if their life is on the line, right, and we're going to receive this data, I want to have zero error. I absolutely do not want to, convict an innocent person, and I also don't want to let a murderer go. I don't want either of these things to happen. So what I'm going to do, though, is I'm going to set my alpha at 99.9. And some people are going to go, no way, I want to be 100%. You're talking about they're going on death row. You can't. I'm sorry. You can't do that. No matter what, you are dealing with a sample. You are always going to have to accept the fact that you could be wrong. You have to get over that. So, but you set it accordingly, and 95% confidence is normal. And then obviously in a situation with life or death, and there are processes that are life and death too, like long or short landings at airports, right? Those types of things, life and death. So you set that confidence, you set that alpha, which gives you your confidence. And then what happens? The prosecution, the defense, they both present evidence. So you get evidence presented to you. This is the same as when you're running an experiment to see if your process is going to be improved or not. If the stuff you're going to do works. So you experiment. And then what happens? Well, I showed you that the computer will give you that little printout there. But then what happens is you can make a decision. You've set your criteria. You've set your decision criteria. So when you get that computer printout, you can make your decision. But it's just like a trial. So that null hypothesis is that you're innocent until proven guilty. Just like that null is innocent until there's evidence. Use better wording. Evidence that says we're not guilty or guilty. Now again, this sample's not over. There's more to this story. In this non-statistical example, the jury decides, let's say they decide there's enough evidence to conclude that the defendant is guilty. Okay, so that means if the defendant is guilty, the jury, or I'm sorry, what did I say? There is enough evidence to support the alternate hypothesis. If the jury acquits, there's not enough evidence to support. And be careful with your wording too. The jury is not saying that the defendant is innocent. We don't know that. We're just saying what words are used in a court of law, which is the same again in our world in statistics. They don't usually say, hey, you're innocent. What do they use? I'm going to start writing it.
Exonerated.
Close. Finish.
Prove beyond a reasonable doubt.
Prove beyond a reasonable doubt. Just like in our testing that we do. You just said, hey, you didn't prove beyond a reasonable doubt. So let's take a look now. When I say that you could be wrong, here's the part. This is where I really want you to understand. And we say set the alpha, right? You saw that on there, set the alpha. That alpha, this is your decision criteria. When we set our decision criteria and we say, well, 5%, we set it at, and we say 5% chance I could be wrong. Well, I kept saying that. And at some point, I'm hoping somebody's kind of pulling out their hair going, what do you mean by you could be wrong? What the heck does that even mean? This is what it means. It means the probability of a type 1 error occurred, which means, let's put that in layman's terms, that means that I reject the null and we say there's enough evidence for the alternate, which means I convicted an innocent person, which means we said there was statistical significance in our experiment and we improved the process in our sim, but in reality, we actually didn't. So when you set that alpha, what you're saying is 5% chance it could be wrong. What do you mean by wrong? Well, it means I might reject the null and say there's enough evidence for the alternate hypothesis when there actually wasn't. And we're dealing with samples. I can never know the true absolute truth. I can't. I have to accept that I might accidentally, not accidentally, I mean, I might inadvertently and not on purpose convict an innocent person. I might accidentally or inadvertently say that we made statistically significant improvements in our event this week, and we didn't. I might inadvertently say, remember this one, let's go back to the one we drew. Team A is equal to team B, the averages for team A and team B. And then team A is greater than team B. This would say, we said team A is actually significantly higher than team B, when in all reality, truth, they aren't. That's what that setting the alpha means. That is the decision criteria that we use when we talk about p-values after the next break. So when I keep saying there's a chance you might be wrong and you have to accept that, that's what I mean. You might reject the null when you shouldn't have. Pause. That's why I do the little processing thing. Remember, you're not tested on green on a lot of this stuff. It's just black. So I just want you to just sit back, relax, and enjoy this. But hold on, there's a flip side to this. We focus in black belt a lot more on this because we just don't have time in green or a beta error. The beta error is the opposite. The beta error says we failed to reject. Remember, those are the only words. We fail to reject the null. And in all reality, we should have rejected it. Which means, let's do this again. The average for A equals the average of B. And then you have the average of A is greater than, the average of B. And we reject it and we say, well, there's no real statistical significance between the average for team A and team B. But absolute truth, which we'll never know, it actually is different. That is a type 2 or a beta error. All right, I think that's quite a bit to choke down right now. We've had a pretty long hour. I'll get through this last couple of pieces that we've talked about already. So here's one of the things that we can do. What's one of the ways at our level? We talk about some really advanced techniques in black belt, but really, how can we handle this? What's the number one thing that we can do to get to decrease both the type 1 and 2 errors? Increase your sample size to a certain extent. We use tools for sample size and all that stuff. And in black belt, we talk about the power of a test and how to pick out the sample size. But when you add more samples generally, you're going to decrease your alpha risk and your beta risk. So that's kind of a go-to answer at a green belt level. What am I going to do about it? Collect some more samples. And then we've talked about confidence interval already. So I'm going to kind of blow past it because we talked about, my average could be between like 490 and 565 for the true population risk. But before we get into probabilities, or the p-value here, we are going to take a break.
So,
right,
so
cool.
I have a question.
Sure.
For the beta, just to wrap that back around, because you were doing the example of like a trial. If you have a beta error, is that the equivalent of letting a guilty man go free?
For the beta, that is, yes, yes. If the person was guilty, and we would let them go, that is correct.
Okay. Okay.
Yep.
Understood.
And so when we start worrying in black belt, since we're about to hit a break, the power of a test, the more powerful the test. So more power, what a powerful test means is our ability to correctly, so basically not have a beta error, that false negative. So when we're talking about power of a test helps us with that type 2 error. Just that's a black belt concept that we do later on. But so when we get into like power, or your black belt starts talking about power with you on a test, it's because they're trying to reduce that beta error. And what's cool is I'll even show you in Sigma XL before the break here real quick. When we say, oh man, how do we figure out these sample sizes? What's going to be the right way to do it? Show you briefly. One of the things that's cool about Sigma XL and or Minitab, whatever you want to do. Oh, sorry. There is power and sample size calculators right here for the types of tests you want to use. So you put in those couple of parameters. And you can, there's a couple of things that we can do in black belt that's really fun. You can either before you collect samples, we can use this and it takes about 30 seconds and say, okay, well, we should be collecting 18 samples or 118 samples or whatever based on the power we want to have. Or you can run a test or you run your experiment and then put what you got in there and it'll tell you how powerful that test was. You have like if it's really bad, oh man, making that beta really high. And sample size and black belt are really, really cool for helping us to figure that out. But again, I wish we had time here, we just don't. Does that answer your question though? Okay, any more questions before the break? I'll put us on a brain break. All right, so where we are now are these p-values. P-values are kind of the last piece of the puzzle that we need. And there's a lot to these that we explore between all the level of belts. So you'll learn this in mastery over the different pieces. But there's really got to be an introduction here so we have an idea of how to make our decisions. Okay, so we said set the alpha, right? That type 1 error, set that I could be wrong. Okay, well, what do you want that to be? Well, I kept calling it a decision criteria. What do we mean? How do we make the decision based on this now? Well, there's a couple things I need to step back first and get us over to our drawings here. And there's a couple of things I want to show you first of all. Do I have any of the spare ones left? All right. So if we're up here, we have different tests that we can run. Okay. We have null and alternate hypotheses of, let's just say, team A equals team B. The alternate is that team A does not equal team B, average. So I'm going to stop there for a second, because remember, when we're framing our problem, there's a couple of ways we can do it. We can do it, is it greater than, is it less than, is it equal to or not equal to? So when we're looking at this alternate hypothesis, the reason this matters is because we're talking about what's called tails. And tails are simply this right here. So the p-value will play in just a second. If I'm saying if it's equal, let's just say the numbers again are 4, it's like 473, I think is what it is. Or 6, whatever. But team B is like 476. Okay. And if we have 476 and then team A pulls a data point of, actually, I'm going to use the one that was actually filled out. So 473 is what team B is, and team A had what? Does anybody remember at this point? I actually do need your help. I'll let you grab it again. 536. Okay. Thank you, Corey. Appreciate it. I wish I'd looked down first. 536. Now, going back to needing this empirical rule here, this is very, very important. Okay. 536, right? 536. Yep. So 536 falls, I don't know, right here-ish. Now, when we look at that, what we're looking at that for that data point for team A, this is team A's point, this is team B's point. What it's saying is that data point there, is that average, that data, is that far enough away from team B to be statistically significant? Would we expect to get that or more extreme? And so when we're talking about tails now, if we're looking at tails, here's what we're saying. We're saying, okay, let me actually, if I could, gosh, I wish I could copy these numbers somewhere else. So if we have this 585, we say, all right, we have 95% confidence, which means we have 5%. Those alpha, that alpha is also called a rejection region. Now, if we are dealing with a two-tailed test, we are going to be talking about 2.5%. What is it, like 2.5%? Yeah, so I actually need, let me see if I can grab these numbers here real quick. I was taking this couple of seconds here to do this. Will make a big difference. So if we copy this data and we got team A and we got team B, cool, cool, cool. Now, 2.5% is right here. And what I say is, look at this 2.35 and this 0.15. Collectively, 2.5% is a rejection region. And what it says is, if I have a two-tailed test, what it's saying is that 5%, so I have 95% confidence, alpha of 0.05, it's saying this 2.5% on this side, 2.5%, this is a reject the null. I just call it a reject the null region. So I remember, reject the null region. And then on the other side, there's another 2.5% for the 5%, right? This 5% that I could be wrong, or it could be more extreme in this case. So if I have the 2.5% on this side, it splits up those rejection regions. Reject the null region. What I'm looking at here is, if I have something that says within a null and alternate hypothesis, if my alternate says that team A does not equal team B, I'm not asking, take a look at that. It says, does team A equal team B? Meaning, does this data point, go back to this light blue, does this data point for team A, is it different than team B? I didn't ask you, is it higher than? Is it lower than? I didn't. I just simply said, is it different? And by saying, is it different, is it not equal to, I have two rejection regions, two tails. I have two tails in which it could be rejected. It could be rejected if it's too low. It could be rejected if it's too extreme on the high end. So it could be one tail or two tails. Now for this one, it's a two tail. So let me copy this again. Now what happens though? What happens? Should have copied it beforehand here. So well, let's take a look at the same thing and we go, okay, but there's 5% to be rejected, right? The 5% rejection region based on what we chose. So we have now in this case though, let's say we scratch this and we say team A is greater than team B. And that's our alternate hypothesis. This is a different test, right? It's asking, is team A greater than team B? This data point, is it greater than team B? Is it far enough? Is it extreme enough to where the difference is not just white noise? It's not just, there's actual statistical difference here. It's not just due to random chance. There's a real difference between those two. That's what we want to know here. Well, in the case where I'm asking, is it less or greater than? What I'm saying is, check this out. Now all 5% is on one, that was 4%, sorry. 2.5% would have been over here. My bad, sorry, 2.5. I wish somebody would have caught me on that. It's saying that all 5% roughly is here. All 5% rejection region. I got to redraw this or it will confuse you. I'm so sorry. I should have bumped this over a little bit. This should have been down here like that. Because you can see that's the 0.5 plus the 2.35 was what, 2.4? Or no, that was, I'm right, that was, sorry. What the heck was I thinking? I was right the first time. Good gracious, my brain stopped. But now what's going to happen though? Now what happens though is now this line is scooted over a little bit because the rejection region is now all 5% of the rejection region is on one side. So now the rejection region's actually bigger on that side. It was 2.5 on each side. Right now it's all 5 on one side. So the reason the tails matter, or the way you ask the question matters, is because the rejection regions are built on those decision criteria. The rejection region is your decision criteria. So asking the question, is team A statistically, or is it significantly higher than team B? That means that is it that extreme or more? And that means all 5% of my rejection region is up on that upper side. Just like it would be the complete opposite if I were to ask, is it lower than? Well, then all of my rejection region would be over here. So the reason this matters in how we frame it, if we go, is it equal to or not equal to? If it's equal to, it's a two-tail test. 2.5% of that rejection region on the upper, 2.5 on the lower. If it's asking, is it greater than or less than, it's either 5% on the upper and all 5% on the lower. If that's what you chose for your alpha. If that's what you chose as your rejection region, if that's 95% confidence, if it was, say, 99% confidence, well, then it would be all 1% on one side or all 1% on the other side. So let me pause there for a second between the two-tail and the one-tail. So two-tail simply means the rejection regions are upper and lower. It's split. One-tail, the rejection regions all upper or all lower. Is it that number, or what I expect that, or more extreme? So what it's saying, so when you ask the question, so when we go back to those 10 points here, that must be down with it. When we go back to these 10 and we're defining our null and alternate hypothesis, it matters. It matters how you frame that question. So that's why you follow these steps like this. I don't just kind of willy-nilly throw it up there and say, here's what I'm going to do. Is this equal or not equal or whatever? What are you trying to ask? So getting used to this, not at Greenbelt, you're just starting out, right? You're learning about it. But I want you to understand, out of all this, if anything just was fuzzy to you right there, just understand that there's a one-tail and a two-tail test. That's what I really want you to get out of this. And that is literally determined by how I ask the question, how I write my alternate hypothesis. So we're going to do a little pop quiz here. Okay, what if I want you to tell me if this is a one or a two-tail. So my null is going to be that team A before changes equals team A's data after we make changes. My alternate is going to be team A before changes is greater than my team A after changes. Is this a one-tail or a two-tail? Okay, I got one answer. I'm going to hold off a second. I got one. Let me see some more. I'm not saying right or wrong until I get a few. Okay, got a 1 and a 2. We got for a tiebreaker. Got another two-tail. What else? So I got 1, 2, 2, 1, 2, 1. Okay, so one of my two-tail people, tell me why you think it's a two-tail.
Because according to your explanation, if something is equal to, then it splits it onto the variation of both sides. It divides that variation by half and it splits it on both sides.
That's correct. If I'm gonna, so, and what I mean by that is the alternate, though. You are absolutely right, but put that in the context of the alternate hypothesis. You're always going to have this as your null. If I were to write this, like, I'll save a lot of time by doing this. If I were to write that and say it's not equal, that would be a two-tail, which is what you were saying right there. That is true. I think you were looking at the null hypothesis and actually kind of making that split. So your logic was all there, but just for these, it's got to be for the alternate. So in actuality, when I'm going to write something like I did before, like this or this, so this is two tail. What is a greater than? And you know what? Let's draw them on there too as we're doing it. Okay, so when I'm doing this top one, the not equals is saying, hey, listen, I got something that we're going to say our center is 10, and I just got, excuse me, I just got a data point that I pulled that's like, you know, right here. I pulled like an 8. What I'm asking is that data higher or lower? Doesn't matter. Is it equal to 10? Is the difference between 8 and 10 just random chance? Is it noise? Well, when we run the test, I'm saying, I don't care if it's higher or lower. I don't care if it's, I can reject it if it's lower, and I can reject it if it's higher. Either way, I'll reject it on either side. If it's too high, if it's more extreme high or more extreme low. That's a two tail. Now, if I were to do this and say, if it's greater than, really all I'm asking is, okay, I pulled a number that is, I don't know, 12. Well, what I'm saying is that greater than? Is it more extreme greater than this average right here? And that's a one tail. Just like if I was to pull this 8 and I just switched to the question and said, is this statistic, is it significantly less than? Well, then I'm concerned with just, is it too low? Is it far enough on the low side or more extreme or extreme enough on the low side that I can reject that null and say, yeah, that's definitely lower than. That's not by chance. That 8 you wouldn't have pulled by random chance. That is statistically significant than 10, different than 10. So I'm going to pause. I'm going to pause here for a moment. Is there, did that come out clear? Well, Siri apparently thinks it did. She came on. Okay, got a thumbs up. Did that clarify though? Hopefully. Like I said, your logic was spot on. Just switch that down. Yep, okay, cool. Is it all good? All right, so anytime we get that not equals to, let me actually run the, let me set the test up and practice it in the real world. Let's do this real quick. Let me grab the B stuff here and I'll run it against A. I actually got to write A on there finally. And I got to use the same size. It's a pain in the butt. I'm not, because I'm not stacking my data right now. So just, I have to run it with just the same size, otherwise it'll yell at me. I can explain that later if we really need to. But what we can take a look at is there's a test we can use. You don't have to know this for green at all. You don't have to know this, but I can run what's called I can run a 2-sample t-test because I have 2 independent samples that are running against each other, and I can see are those means statistically significant. And just so you know, they're unstacked. Again, if you ever work with this data, I don't know why it's like, there we go. The data is not stacked on top of each other. It's not all in one column. So I'm just worried about the, walk you through some explanations. So on the video, if you go back through and data's in their own column, right? They're not on top of each other. So they are unstacked data, and I'm going to look at lead time versus A and B. And I want to see, is there a difference between their means? Now, the reason it says, are the means different? Is it equal to 0? Because it's seeing, is there an actual difference? I mean, in a perfect world, they'd be the same mean, right? So it's just saying, hey, is the difference between these two 0? Or is the lead time A greater than? Or is it not equal to? Or is it less than? Well, let's start from the top, not equal to, and we want 95% confidence. So since I'm doing is lead time for A not equal to lead time of B, is that 1 or 2 tail?
Not equal to is 2 tail.
Correct. Excellent. And I saw Corey put it in there too. Yep. And now I'm seeing, there you go. There you go. See, a little more practice. It's all good. And we got 2 tails. That's because I'm not asking, is it less than or greater than? I'm saying, is it too far greater than or too far less than? Could be either, which means I have 2.5%, right? This 5% is split between the upper and lower. What if I ask, is lead time for A greater than team B? 1 or 2 tail? 1 tail. There you go, Corey. Thank you. 1 tail. all 5% rejection regions on one side. So let's just ask that because team A is actually higher. So let's take a look and see if it's significantly higher or if the difference between the two is just noise, random chance, sampling error, whatever, but there's no statistical significance. Well, let's take our time to actually write out the null and alternate hypothesis again, which by the way are right here. So our null hypothesis again is that team A equals the average from team team B. And then the alternate is that team A is greater than team B. We selected 95% confidence, which means we ended up, I'm using this for alpha from now on in A because it's just easier for me to write. So we left ourselves with a 0.05. Now what we do for that p-value, this is the final piece before we can finish up with the stats piece. So this is our decision criteria, and we compare that to our p-value. So is this p, is it higher or lower than 0.05? Low, that's right, p is low, which means null, however you want to remember this, null must go. P is low, null must go. P is low, the null must go. Is team A statistically or significantly higher than team B based on what we just did? Yes or no? So P is low, the null must go, which means that we reject the null. I'll check the chat in just a second. We rejected the null and support for or evidence for the alternate. So what does that mean? We got 3 no's. The P is low, the null, we rejected the null.
So if we're rejecting our primary hypothesis, then the alternate is supported.
Correct. Which means, is team A significantly higher in their average than B?
Yes.
Thank you. You are absolutely 100% correct. That is right. So putting all of these pieces together, this is how we run those tests like that. So all this stuff that looks oh so confusing is actually, it's hopefully, I'm gonna get rid of this, it's actually not. So let's go back to the normality test then that I ran. We're gonna look at the normality test for which team is this? This is team A. So let's take a look and set up our null and alternate hypotheses. Our null hypothesis says we have normal data. Normal data. And our alternate hypothesis says we have non-normal data.
Hey, sir, could you go back to that other slide? And the only reason I'm confused is I understand if P is low, the null must go. But if the alpha is 0.05, but the P value is what looks like to be 0.006, that's a 100,000, or I'm sorry, that's a 1,000% difference. So the 0.05 is significantly higher than the 0.006. So
right, you compare, sorry, it goes off from that P value. If the P is lower than significance, the P is low, the null must go. If the P is high, if the P is higher than the alpha, then the null will fly. Yeah, it goes the other way. It's based on the P value. I think you're kind of switching, like I'm comparing the alpha to the P. It's actually the P to the alpha. It's based on, is the P low, null must go? Yeah, I think you have it in your head. Let me tell you this, your logic is right on. I think you just have it flipped in how you're seeing it.
Yeah, story of my life.
I think what he's saying is the difference of the P value being lower is so small that is it significant? Is there significance in the fact that it's lower and the fact that it's so much less lower?
All that
Sorry.
Kind of all that really matters is the P lower than than your alpha or not? Is this P value lower than this? That's really all I care to see at this point. And so that's just how we make our decision. That's like literally that's before we go into the test. Let me go back to the 10 steps real quick. So when we go back to the 10 steps, that's why before we ever run the test, we determine what we want our alpha to be, because that's kind of our line in the sand that says that's our decision criteria. When that p-value is spit out, I'm going to compare it to that alpha. And that's how the decision is going to be made. No gut feel or anything. We determined before we collected it, well, not necessarily collected data, before we ran the data and before we ran the test, we determine what that alpha is so that we don't manipulate it and we don't say, well, is it close? Is it far? No, you say, is it higher or is it lower? Granted, SMEs, there's always course as we get black and master black belt, you know, is it really close and should we have a conversation? But for the sake of green belt, it's either higher or lower. That's it. Is the P high? Null will fly. Is the P's lower? Null will go. P is low, null must go. And you keep it pretty simple like that. That's why we developed that decision criteria beforehand. So we have something to say when this data comes out, here's what I'm making my decision based on. Does that make sense?
Yeah, I think I got it now. I appreciate it. Thank you.
Okay. Yeah, no problem. No problem. I don't think there's anything wrong with your logic. I think you just had the which one to compare to might have been backward, but sounds like you got it. So that's cool. We're going to run the normality test. Sorry, after this. So if we're going to remember, we said we can either you can look at the data and determine, well, is it normal? Well, a lot of times we can't tell, right? Like this one here, we couldn't really tell. Well, let's come back now. We did one earlier on, and I said we'd unpack this throughout. Well, now you can help me interpret this one. Do we have normal data? Well, let me finish setting the test up. We want our 95% confidence because that's what it was run at, which leaves us with an alpha of 0.05. So is this P higher or lower? P is high or low. Is what? Is that P value higher or lower than 0.05? Yep, I'm seeing higher on a couple. Okay, so P is high. The null will fly. Do we have normal data? See, you guys got this. You got this. These tests look so intimidating, but they're not. Your decision criteria is right there for you. You made it. You were the one who determined that 95% confidence, the alpha 0.05. I could be wrong, right? It's possible. So there you have it. Get ourselves caught up on the slides here real quick. We covered all the p-value stuff. And we also talked about this if it's critical. When you said that 0.05, that alpha being 0.05, the 5%, that's just for normal processes. It doesn't mean it's arbitrary. 0.01 if it's reasonably critical for safety, and 0.001 if it's life versus death. Those are rules of thumb. Your organization will tell you, you will not be determining, most likely as a green belt, if this is 95% and what our confidence is. There should be criteria set by the organization. And then there's going to be for that particular process too. I mean, most times you're not going to be just making it up. If you do, if it's not life or death or it's not too critical, just simply default to 95% confidence. All right, in this last section, we're going to be talking about stability, normality, stability, capability. The last parts, we did normality. Normality means do we have a normal curve, right? That's shape. But let's talk about, is our process stable? And there's something we're going to use. Let's see, a stable process is much easier to study and improve. And that's a book that I actually love. It's in my drawer right next to me here. I've actually read the book cover to cover, believe it or not. But a stable process is much easier to improve. So let's talk about what does stable mean? Stable means that we're producing consistently. And there's actually a chart that we're looking on here. Are we stable? Are we making the product or service pretty stable, or is there a lot of variation and a lot of funny looking variation? When I say that, let's take a look at the data. This is your stability chart, like the ones on the top and bottom there. So just by looking at these stability charts, are we stable? Well, let's talk about that for a minute. And stability, by the way, we've listened to the specification limits are given by the customer. That's the voice of the customer, right? We've talked about that. We've also, at this point, talked about the voice of the business, you know, what's happening with the business, but we haven't heard from the process yet. When you're doing control charts, which is what these are called, control charts, these are actually the voice of the process. So when we input that data into there, all those different lead times that you had, This is all of your data listed out in a time series, and we're going to focus simply on what's called the IMR chart today. There are like 7 different charts that we can choose from when we're looking at stability. See, there's control charts. All this stuff has to do with these control charts. So we can choose all sorts of different types of control charts. But today I just want you'll get the concept. If you get one of them, you'll kind of understand the concept for all of them. The one that we're going to focus on today is the individual moving range, IMR. Individual, I know it's a little hard to see on this side here. This is every individual data point listed out in its series, right? This is point 1. So if we looked at the data point 1 is 390, point 2 is 466. So let's go see that so we can see what we're talking about. Point 1 is 390, point 2 is 466. So that's what that capability report is, right? It's telling you what each of these data points is. That's literally it. Well, what's important though, to figure out if we're stable and we're producing consistently or not, this is going to take a couple of concepts we've learned so far. First of all, the voice of the process is going to give you the mean. We've been looking at this for quite a while. It's 536. We've seen that. I'll make it a little bigger for you. So this is 536. Now, this is actually called the lower control limit. So lower control limit, and this is called the upper control limit, hence the control chart. So upper control limit. And these numbers here, these are +3 standard deviations from the mean and -3 standard deviations from the mean. And now that should mean something to us now, because think about if we just took a normal chart here, I'll draw the normal distribution, and we use our handy dandy empirical rule. Do we remember how much data or how our data, we had drew 3 standard deviations, would we expect to fall between those lines? Let's take a look at a clean one.
99.7.
99.7. Okay, so our control charts are based on 3 standard deviations above and below the mean, which means what it means is these control limits here being plus and minus 3 standard deviations, we would expect 99.7% of our data to fall between those control limits. So right, it's just kind of if you look at it, it's just like a little normal curve on its side there. We'd expect 99.7% of our data to fall between our upper and lower control limit. So when something doesn't fall within our control limit, that's when we go, all right, Houston, we have a problem. Something happened here, because we would expect 99.7% of our data to fall within plus or minus 3 standard deviations in the mean. Well, we have a point, something that lands outside of there. So very important for an exam is that you would call this special cause variation. And special cause variation means, or the answer for this is we have to investigate what happened. This is actually point, let me see. I don't know what point that is, like 6 maybe. So that's 0.6. So we would go back and take a look. All right, that'd be line 7 technically. What's going on with this? Why was this so high? Oh, it must be this one, sorry. So why did we have a 795 for Marty McFly in that round? What happened? And we're not going to answer that right now, but what you would do is you would investigate and say, why do I have special cause variation? Why do I have variation in my process that I wouldn't expect? Like that, what's happening there? Do I need to make some sort of fundamental change? Or do I just work with that? Do I fix that data point, find out what happened? We make sure it doesn't happen again and we're good to go, but we have to investigate and figure that out. Another thing we can see on these control charts that's very helpful. Look at this trend. You can clearly see a trend. First of all, variation getting tighter and then time going down. Why do you think that happens?
As more packets get to you, you start the backlog.
Well, the backlog will build up and cause more time. This is learning curve. You're getting better at your job. So on a control chart, there's a lot of information that we can see here. So on these individuals, we look and go, man, there's a trend. So looks like learning curve was pretty huge because it actually got faster. And then what also we recognize is you notice it keeps going up by 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4, 5, 6. Yeah, that might sound familiar. you can see that 6 keeps repeating itself. What that is, that's because you're putting them in batches. And so there's like a little bit of a queue, and it drops off in a new set. A little bit of a queue, drops off in a new set. So batching seems to be an issue here, putting them in 6 at a time. But the idea is this control chart gives us so much information. This little chart here reveals so much about our process. And this is the one not saying, are we capable? We haven't done that yet. This is simply saying, are we stable? Are we in control? And the answer for this process for team A is no. Anytime you have special cause variation, there's some other rules you learn later on in your career, but anytime you have this special cause variation or these nasty trends, you're not in control. And it's hard for me to make inferences and talk about capability and stuff when I'm not in a state of control. That's what that textbook was trying to tell you. Well, let's look at team B. Oh, and I'm sorry, on the bottom, since you have your individuals on top, what you got here is your moving range. Oh, sorry, your moving range. And what this is if you notice, there is no data point 1. Because on the bottom, what this is this is showing you the first data point is the range or the difference between point 1 and 2. The difference between point 2 and 3. The difference between point 3 and 4. The difference between point 5 and 6. 6 and 7, 7 and 8. So it's the range between the two points moving down. So that's why there is no number 1 there, because there's no range for number 1. It's first one in. So the top is individual, and it has this is your time with your mean up here, your average for your lead time. And on the bottom here, this is your moving range. So once again, you would look at this data point here and go, okay, so what happened here? This is the data point. Probably have to get rid of it so I can actually get onto it. Point like 10. So there was a difference. Oh yeah, see right here? There's a huge difference, even though it's a drop. And you'd investigate and say, well, what in the world happened there? Why was that range so huge between those 2 data points? I can already tell you it's because it was between run 1 and run 2. Just FYI, remember, because we got 9 on round 1 and 9 on round 2. So that's the difference between ending one run and then getting into the next run. But my point with this is that you look at this and say, okay, what's going on here? Why is this happening? And as you can clearly see, that trend continues. This is the difference between the next set of runs. So you're seeing those spikes when a run ends and then the next one starts. Pretty cool. Let's take a look at team B, and so we can do this again and walk through this. Now, team A or team B actually, ironically, had the opposite trend. Team B had a trend where they kept getting slower and slower as they were going, like they said, because queues were building up and stuff. So they were trending upward. And so let's take a look here. The individuals, you got your +3 standard deviations, -3 standard deviations. Again, you would expect, drawing this kind of do the best I can, the 99.7% of the data you'd expect to fall in that zone. So let's take a look. Let's go back to our highlighter. We have this point here, the couple at the end. So you can see that we have an issue where we trended slower for team B, which is the opposite of the learning curve. Actually, that means that like somebody had jumped in and said the queues were getting bigger, which means it was taking more time. And the point is, not the fact that I just analyzed that, but you would go and take a look at that and go, why are we continually getting slower? Why is there a trend? Well, that's what you have to figure out tomorrow. That's why you need this chart to show you that. Unless I showed you that, you probably wouldn't realize it. It's visual and right in front of your face right now. Let's take a look at the moving range on bottom. Well, ironically, you don't fall out on the moving range. It's pretty big ranges, but you're not too bad there. So you take a look and say, all right, what's going on? Why are we getting slower? And that's something you're going to have to account for. And so remember, this part right here is simply answering a question of stability. Are we stable and in control? And the answer is no. You have special cause variation. These, anything outside of there, like I said, is called special cause. Remember that for an exam, variation. Just like on the other, just like Team A's. Team A has special cause variation. So when we're analyzing this data, these control charts are wonderful, and you're going to see these again at the very end when we do a control plan. Because the whole point is, remember, let's go back to this slide because this is so unbelievably important. A stable process is much easier to study and improve because it's predictable. It's stable, it's predictable. It's much easier for me to improve that rather than something that's all over the place. So a stable process is much easier to improve. Very, very, very important concept. And I've already drawn all this stuff for you, by the way, just so you're aware. So this is taking a look at your control charts. We will study these again on late Thursday afternoon. We'll go over, this is our before data. We'll compare this to our after data. And so we'll look at these same charts again briefly and say, all right, are we more stable now? Are we faster now? Are we more capable now? Because we got to answer one more question yet today. I'm going to hold though a second. How's everybody feeling about these control charts, being introduced to them? These are some of the most powerful weapons in your arsenal. Good? Okay. And like I said, I'm taking all these notes and stuff and writing this for you so you'll have it. You have access to this. I will give it to you. So you don't have to try to copy all this. Here's the thing. Even if we were stable, let's say we're stable, like pretend. Being stable doesn't mean we're capable. Because the ultimate question in the measure phase is, are we capable of meeting customer expectations? Expectations. Okay, that's what we've got to figure out. Are we capable of meeting customer expectations? Yes or no? This is actually, I would argue, the easiest one of them all. So all those concepts we just built up to was to get to this point right here. We've done p-values and hypothesis testing, descriptive and inferential statistics, right? We've done all this stuff today to answer this question. Are we capable of meeting customer expectations? Now, those customer expectations are pretty simple. That's 90 to 180 seconds. That is our control chart in the upper left-hand corner there. So even just by physically looking with your eyeballs, your calibrated eyeballs, are we capable of meeting customer expectations for, was this Team A? Are we? Nope. Let me give you something that's very, very helpful. You know, we used to have to know all of these, or, you know, how do you do CP and CPK and read all these? You know what? We'll do that in black belt because it's required for your body and knowledge. Screw that. Watch this. Well, let's just take a look. How did we perform? Easy. 100% of them fell outside of the upper spec limit. Not real hard to interpret that, is it? Not hard at all. I have a simple thing. Go ahead.
For clarification, when you say, are we capable of meeting customer expectations, you mean, are we capable in our current state of meeting customer expectations, right?
Yep, this is, we're still,
current state.
Yep.
Got it.
Mm-hmm.
Okay.
Yep, in the measure phase, we're answering that for the current state. Great question. Great clarifying question. Are we capable of in our current state? Nope. And then I kept asking you that one question at the beginning. Well, then how far off are we? There it is. We're 100% off. 100% of our data falls outside of our upper spec limit. That's how far off we are. And now we say, well, what the heck are we going to do about it? That's the next class. Let's get to the root cause. So let's take a look at Team B. All right. And so I'm just going to put capable because I'm giving you all both data. So you can look at the slide before, so I don't have to handwrite it all. Are we capable of meeting customer expectations? What do you think, Team B?
Yeah, it's not going to happen.
Very dry. I like it. No. How far off are you?
A smidge.
Just a hair. 100% fall outside of the upper spec limit. So all of that hard work today, getting to the stats, all of that led to this moment. right here. Are we capable of meeting customer expectations? All that data we've looked at today, all the hypothesis testing, all of everything, like getting to understand our standard deviation, how much variation we have and all that type of stuff. All that led to this moment. Are we capable of meeting customer expectations? Team A, nope. 100% of our packages fell outside of the upper spec limit. Team B, nope. 100% of our packages fell outside the upper spec limits. Now, what are we going to do about it? We're going to move to the analyze phase. We're going to start looking for the root causes. Let's head back here, because now the other math formula here. Now we're headed to this, because I want to know, why am I not capable of meeting customer expectations? So what we got to do is get to the root cause and explore which variables are causing the variation in our process. Which steps did you identify that are causing waste in our process? And then in the improve phase, what are you going to do about it? Game, set, match. That's the measure phase, y'all.